In this video lecture, I'm going to cover the ideal gas law. So we first need to talk about what the heck is an ideal gas, because how does that apply to the ideal gas law? An ideal gas is basically a gas that follows the four principles of the kinetic theory of gases that you learned about at the beginning of the unit. An ideal gas basically removes a lot of different variables that would make mathematical calculations really difficult for us to complete. So, like the first principle of kinetic theory, the kinetic theory of gases says that gases consist of tiny particles that are separated by large distances, which basically means that the volume of the gas particles themselves compared to the amount of volume or distance between the particles makes the volume of the gases themselves negligible. So therefore, the volume of the container is the volume of the gas. We don't need to factor in the volume of the gas particles themselves. Am I going to ask you about this stuff? No. AP Chem will. So I'm just giving you a brief overview. Gas particles are constantly moving. We know that they're also hitting the sides of their container, which is what we measure as pressure. The velocity of gas is related to the temperature. Gas particles do not feel any forces of attraction or repulsion with each other, or in other words, they don't form IMFs with each other. And so that removes things like gas particles potentially clumping together and the pressure being different than what you expect and all this stuff. So really, an ideal gas is ideal because it removes a lot of variables that would make mathematical calculations very difficult. Okay? So this is the ideal gas law. It's PV equals nRT. A lot of students like to call it PivNert. So if you enjoy that, you call it that, you go for it. The variables in the ideal gas law, R is a gas constant. So that's the only new variable that I'm throwing at you right now. That's a constant. It's going to be something that relates all of the variables to each other. And the number for that is 0.0821 liter atmospheres per mole Kelvin. The units on our gas constant are going to dictate the units for our other variables. They need to match up with the units in our gas constant. Okay, so our pressure has to be in atmospheres. Our volume needs to be in liters. N must be in moles, it can't be in grams. And T must be, or temperature must be, in Kelvin. If you don't have any of these variables in the correct unit, you are not going to get the correct answer, and your units would be messed up. So let's look at an example problem. It says to determine the temperature of 2.49 moles of a gas contained in a 12-liter vessel at a pressure of 1.41 atmospheres. Let's pull out our known variables. We have a mole value of 2.49 moles, a volume of 12 liters, a pressure of 1.41 atmospheres, and our unknown is the temperature. We can literally just plug these directly into our ideal gas law. So I plug in the pressure for P, the volume for V, that's equal to our moles for N, R is our gas constant, and we're solving for T, so I put an X in for T. Hopefully we can solve this for X. Yes, we can multiply these two numbers, and then divide the two to get X by itself. And you should find that the temperature comes out to 82.8 Kelvin. Sig fig wise, again, you're lucky. We are multiplying and dividing, so you can just look at the total number of sig figs and all your starting values, and whichever one has the lowest number is how many total sig figs should be in your answer. So we have 3 here, 4 here, 3 here. This will have 3, so our temperature should have 3. Looking at a second example problem, a deep underground cavern contains 2.24 times 10 to the 6 liters of methane gas. Methane is CH4. At a pressure of 1.52 atmospheres and a temperature of 315 K. How many grams of methane does the cavern contain? So to pull out the numbers we know the volume is 2.24 times 10 to the 6 liters. It's up here. The pressure is 1.52 atmospheres. The temperature is 315 Kelvin. And we need to solve for N, which will be moles, that we can then convert into grams, which is what the question is asking us for. So I can plug those numbers into my ideal gas law. Pressure, 1.52 atmospheres for P. My volume in for V. I'm solving for N. I have my gas constant in for R and my temperature in for T. I can solve for N, which comes out to be 1.32 times 10 to the negative 7th. Rounded to 3 sig figs because all of my starting numbers actually have 3 sig figs this time. But that's moles of CH4. I need to convert it into grams of CH4, so I'm going to set up a compound stoich problem here. Plug my moles of CH4 in the upper left-hand box, bring moles diagonal down. There's 16 grams in 1 mole of CH4, so I multiply these two to find that there's 2.11 times 10 to the negative 6 grams of methane in the cavern. Should probably good because that is flammable. So cool. For the check for understanding number 1, I want you to pause the video, try and solve it yourself, and then hit play when you're ready. For this one, plugging our known values, or taking them out, I should say. I have something related to N. I don't have N directly, but I have 5 grams of H2, which I can convert into moles. I have a volume of 50 liters and a pressure of 1.55 atmospheres, and I'm asked to solve for T. So first, let's convert that 5 grams into moles using compound stoich. So you should have put 5 grams in the upper left-hand box, gone down with 2 grams in 1 mole of H2. So 5 divided by 2 gets you 2.50. Rounding to 3 sig figs, because our 5.00 has 3 sig figs. We can now plug everything into the ideal gas law. Pressure in for P, volume in for V, moles of H2 in for N, our gas constant in for R, and then we're solving for T. And when you solved it, you should have found the temperature as 378 Kelvin to 3 sig figs because all of your numbers have 3 total sig figs to them. For the second check for understanding problem, I want you again to pause the video, try and solve it, and hit play when you're ready. Our known values out of this were our volume as 2.20 liters. Our pressure is 1.01 atmospheres. And the temperature provided was 37 degrees Celsius, which we needed to convert into Kelvin, so I did that by adding the 273. I put a decimal at the end of the 310 to show that this number should have been rounded to no decimals. So the 0 is significant still, and the decimal shows that. And I was asked to solve for N, which really then we need to convert into grams because we were asked for grams. So let's plug all those numbers into our ideal gas law. We have our pressure for P, our volume for V, N is what we're solving for, R is our gas constant, and T is for temperature. When you solved for N, you should have found that it was 0.0873 moles to 3 sig figs because every one of your numbers has 3. But I need to convert that into grams, so you should have done compound stoich to convert moles of air into grams. And they give you the molar mass of air because air is a mixture. It's made up of O2, N2, CO2, lots of other stuff. So you should have put the moles in the upper left-hand box, gone down with 1 mole, and up with the 29 from the problem. It's kind of an average of all the different gases that are in the air. Multiplied the two to find that you have 2.53 grams of air in the child's lungs. And that is going to be it for the ideal gas law.